In modern dynamical systems, there is an ongoing effort to bridge standard real-world dynamics with higher dimensional arithmetic geometry. Our baseline is exactly this, the real transfer operator, denoted p hat sub s. It governs the observable, macroscopic behavior of our dynamical system. Beside it sits a proposed higher-level counterpart, the mixed adelic operator, p sub s. This operator incorporates both real continuous math and discrete p-adic arithmetic. Establishing a connection between these two scales requires strict mathematical proofs. We cannot rely on analogies. We have to seamlessly map functions between the real domain and the p-adic domain, ensuring the underlying dynamic information remains strictly intact. If these two operators lock together structurally, it proves that the real-world dynamics we observe are actually localized projections of a broader arithmetic reality. But this raises a specific diagnostic question. Does the finite adelic state actually contain unique dynamic information? There is a risk that the adelic mathematics might simply be a scalar dummy variable. In this context, a dummy variable is an adelic normalization dressed around an essentially real operator. It looks complex, but computationally it cancels out completely. To refute this, we have to clear three hurdles. First, we must rigorously construct the infinite-level adelic operator, k sub j, on the bounded space L2 of z hat. Second, we have to confirm the exact marginal identity. Mapping a real state up to the mixed space and back down must perfectly recover the real operator. Finally, we must demonstrate genuine mixed-place coupling. We need proof that the arithmetic states actively dictate the real-world projection. By satisfying all three conditions, we confirm the p-adic math is an honest dynamical participant, rather than a mathematical mirage. Before we can test for coupling, we have to guarantee the operator mathematically exists at the infinite limit. We begin by constructing finite-level p-adic cylinder approximations. These act as discrete grids, mapping the state space at specific depth levels, n2 and n3. As we increase the level n, we test for refinement compatibility. The larger blocks must subdivide cleanly into denser configurations. Exhaustive computation shows this refinement holds strictly at every tested finite level. Because the compatibility is exact, these discrete approximations lock together, allowing us to transition safely to the dense subspace of locally constant functions. This defines our target infinite-level space, L2 of z hat. We then audit the conditional probability mass. Across all tested cylinders, the row sums never exceed 1. This strict mathematical boundary confirms the system acts as a genuine L1 contraction on the locally constant subspace. Using standard density arguments, this contraction property extends the system into a fully bounded operator. The infinite-level operator, k sub j, is now rigorously constructed. We have a stable mathematical arena to test the real-world connections. Now we tackle the second hurdle, verifying the vacuum state identity between the real operator and the mixed adelic operator. We start with a real state, f. An embedding function, iota, attaches a standard spherical vector, lifting f into the mixed adelic space. Next, we apply the full mixed operator, p sub s, to this embedded state. Finally, we apply a marginalization operator, m sub f. Integrating over the Haar measure projects the transformed mixed state back to the real domain. For the theory to hold, this pathway must yield the exact same result as applying the real transfer operator directly. We track this algebraically by applying the formula m sub f, p sub s, iota to the real function. The critical step is integrating the adelic operator component against the Haar measure. The target cylinders are internally non-uniform, but when integrated, that variance collapses. The integral yields exactly 1/27th for every single branch. We then introduce the designated weight factor built into the mixed operator, 16 e to the negative s phi 3. We multiply our integral, 1/27th, by this specific weight. The result is exactly lambda inverse e to the negative s phi 3. This is precisely the prescribed weight of the real operator. The vacuum identity holds exactly on the dense core. The complex adelic system flawlessly shadows the real dynamics, but an exact identity doesn't resolve the collaborator's main concern. The adelic math could still be a passive normalization artifact that just happens to balance out. We need a diagnostic test that isolates the finite adelic source state. We set the parameters. We select two mathematically distinct source cylinders, but ensure they have an identical Haar mass. If we run both cylinders through the operator and their real-world projections match, the system is only reading their mass. The idyllic state would be a dummy variable. However, if their real projections diverge despite having equal mass, it proves genuine mixed-place coupling. The computational ledger evaluates this at a specific finite depth, n2 equals 2 and n3 equals 2. Out of 36 equal mass source cylinders tested, 27 returned a projection of exactly 0. The remaining 9 cylinders yielded a common, strictly non-zero projection. This sharp 0 versus 1/27th split proves the output is non-uniform. The finite idyllic state actively alters the real-world outcome. So what exact mathematical mechanism forces this split? The ledger traces the cause down to a severe structural asymmetry between the two-adic and three-adic valuation laws. Look at the two-adic factor, defined by a valuation law of 4. It is strongly contracting. Because of this contraction, it collapses all variation into a single deterministic outcome at this depth. Now contrast this with the three-adic factor, where the valuation law is -3. It is expanding. This expansion spreads the source dependence across multiple distinct residues, directly generating the split in the output. Because this expanding mechanism functions at infinitely many levels, specifically any n3 less than 3, the coupling transfers directly to the L2 space without needing further approximations. The construction is fully realized, the infinite limit is well defined, the vacuum identity is exact, and genuine mixed-place coupling is proven through arithmetic asymmetry. The analytic realization is an honest dynamical participant.